We've got 17 here and another half a dozen on YouTube.
Okay.
So what I'll do is I'll mute everybody. And Danny and Samuel, please unmute yourselves.
All right.
There we go.
Okay, that's me unmuted. Samuel, I'll just do a couple of very quick initial announcements and then bring you in. Are you okay at the moment to go? Yeah.
Yeah, no problem.
Radio. Okay. Well, good evening, everybody. Welcome to the June Irish Astronomical Association meeting with our guest speaker, Dr. Samuel Grant from QUB. Just a couple of quick mentions before I hand over to Samuel. Tentatively, it looks like things are gradually coming back a bit more to normal with a couple of recent openings and various other developments. You probably heard in the local news as of the 2nd of June, just passed, the new Dava Dark Sky Park and Observatory opened officially. And a couple of us, Terry Mosley, Adam Jeffers and myself went down to witness the event and to demonstrate our new rocket launching equipment. It's the compressed air, water powered launcher for bottle rockets. And we intend to use it some of our public events in the future. It's quite a draw, especially for youngsters. So Dava is open, and without needing to be political, I hope it stays open longer than the guest of honor who carried out the ceremonial down there that day. The second establishment, Armagh Observatory and Planetarium, will be open as of this Saturday, 26 June. Further details of what is available and what they would like to do would be, of course, be on their website. There are many other things, as Jerry has alluded to, and I would recommend that you keep an eye on Terry Mosley's invaluable frequent bulletins and, of course, our own website, the Irish Astronomical website, irishastro.org. One last internal thing, our annual general meeting scheduled for 18 August. So there will be one post change, our secretary. We already have a volunteer, but keep an eye on that for further details. All right, moving to our guest speaker, Dr. Samuel Grant, who works at the Astrophysical Research Centre in Queens. And his talk will be on the diverse future of solar physics. A few details about Dr. Grant, if you're not familiar with him. He is an STFC postdoctoral research fellow employed at Queen's with a focus currently on wave activity and energy transport in the lower solar atmosphere. Dr. Grant obtained his PhD at Queen's under Dr. David Jess after doing undergraduate studies at Glasgow. And until September last year, he was employed as a lead researcher in a slightly different field in the industrial collaboration to advance biomedical science through the application of astronomical techniques at QUB Randox Laboratories, which I hope will be of benefit considering the current situation. And with that, I hand over to Dr. Grant. Okay.
Yes, great. Well, thank you for having me. I was only thinking today that my first interactions with these seminars were keeping the door open for you when you would come into the physics building. So I never thought I'd actually end up speaking at the same events that I was propping the door open for. So my goal from what Terry had sort of asked for me to do was I've aimed for a more sort of general discussion really on where solar physics is now in 2021 and where we're hoping to go. I would try my best to be general, to not leave anyone behind with jargon. Though if at any point I'm going off on a tangent or I'm enjoying myself talking about my own research interests too much, feel free to put something into the chat if there's anything that's totally unclear. Otherwise, I've left my contact details at the end of the slides if you want any further links or more discussion on what I'm talking about tonight. which really the idea behind it is, first off, really to discuss, where is the sun itself in 2021, and not where it is in the sky, but more where we are in terms of its activity cycle, what we're expecting to see when we point our telescopes at the sun, where that's going to go in the 2020s. That all has strong relevance when it comes to actually building telescopes, sending satellites up into space. You want things to actually look at. So we'll discuss the solar cycle, the implications of entering into cycle 25, moving into really where the observing suites that we're using are heading in the 2020s, with some of the new very expensive observing suites that have been recently deployed. And yes, I hope to at the end just touch on some of the applications that we've had to our work in recent years with Randox in a manner that doesn't break any embargoes. But by all means, the work became a lot more relevant come March of 2020 than I think we thought when we started the project in 2017. So to begin with, really, when we're talking about where is the sun in 2021, what's it up to, how active is it? We measure the activity of the sun based on its magnetism, on how much of its magnetism we can see and how magnetically active it is. The solar magnetic cycle, as it were, the strong magnetic fields that we see in the sun, are actually thought to be caused by a relatively simple dynamo effect, something that you might see in a wind-up torch or something quite simple, with measures of differential rotating plasma creating magnetic fields. In this video that I'm showing here from NASA, it evidences the fact that the sun itself isn't a rigid body. It's a loose collection of plasma of varying densities. So when it's rotating, the plasma at the equator will rotate at a faster rate than that at the poles. So if you see in the color scheme of the cutout, we have blue being your quicker rotating motions, red being the slower. And this rotation, this differential rotation, is what winds the magnetic fields of the sun up and starts to create some of the more exciting fields that you would see if you were to point a telescope or even just look at a solar image itself. Sunspots being the most common evidence of the magnetic field of the sun. And as that twisting happens, what this video here shows is these fields get twisted, intertwined, and when they have enough potential energy in them, they can break through the surface and form the sunspots that we all, in effect, know and love. Sunspots themselves are the way that we actually practically measure solar activity, and just as simple an act of counting how many sunspots are on the disk at any one time and making measurements based on that. So the more sunspots you can see, in general, the more magnetically active the sun is at that moment in time. That breaks us into what is known as the solar cycle, which I'm sure many of you may have already heard of. For those that haven't, if you take that simple measurement of the number of sunspots on the solar disk at a given time, it becomes very easy to see with your eye that over periods of decades, of centuries, there's a very distinct 11-year pattern to the appearance of sunspots. You get peaks and troughs in a very, very distinct pattern. Now, through various research formats, in the modern day, for instance, we can just count using telescopes, using satellites, but people have used the historical works of previous astronomers dating back to the 1600s, where they counted by eye. And then even further back, I've actually been able to look at the carbon rates within trees to get about a 12 to 13,000 year record of the solar cycle in an accurate way. And it all follows this pattern that you can see in the plot in the top here, that you get these very distinct peaks and troughs in the amount of sunspots that you'll see on the disk over the course of 11 years. The reasoning behind this is actually that it is part of a longer 22-year cycle, wherein the sun, like any normal bar magnet, has a north and south pole of different polarities, and that those polarities swap every 11 years. So your positive becomes your negative becomes positive. Not going to go into the details of why. Again, as with all things, as Terry was saying earlier about the cosmologists, it all boils down to maths in the end, and maths doesn't make a great Zoom call. But what that is that this solar cycle is actually superimposed on a larger 22-year cycle that is very well understood. The importance of the solar cycle really to us, both as astronomers and people who just inhabit the Earth, is that solar activity is directly related to flares and then to coronal mass ejections. These are your very explosive, very energetic events that can cause significant damage to the Earth if you have a Earth-directed CME. These charged particles can bash off the Earth, can cause estimated trillions of dollars worth of damage to our electrical infrastructure if a certain strong CME was to hit in just the right way. So the solar cycle is closely monitored, closely predicted for that reason. If you're at a peak of a solar cycle, then we're going to get more flares. We're going to potentially have more CMEs. Now, if you're looking to protect your infrastructure, if you have satellites in space, you want as little activity as possible. But if you're a solar physicist like myself or an astronomer like you want more activity. More activity means more things to look at. So there's a bit of a diverging view on the solar cycle, with those who have money invested in it wanting as little activity as possible, and those who are employed to look at the sun wanting as much as we can get. So off the back of that, there's a lot of interest in predicting these cycles, trying to work out what's going to come next. Is the next cycle going to be stronger? Will it be weaker? What are we going to see? And if you follow astronomy in the news, you'll see that sometimes it can lead to slight hysteria. This is a headline from the Washington Post recently about a paper that sought to predict the next solar cycle 25. And I put it up simply because I don't think I've ever been described as a maverick astrophysicist before, and I'm not convinced there are many of us. But as you know, with the mainstream press, they'll spin just about everything into just about as exciting and as sexy as they can get, really. But the idea behind the general interest, at least in the early 2010s in the solar cycle, was the worry of a Maunder minimum appearing. So around the early 2000s, we started to see a marked decrease in the strength of a solar cycle. So the number of sunspots you would see at the peak was dropping dramatically. And around the time I was getting into solar physics as a PhD student, there was some concern that we were heading for a large trough in magnetic activity in the sun. It's called the Maunder minimum because, as you can see from the plot at the top, there was a period of about 70 years from the mid-1600s to the early 1700s, whereby there was limited to no solar activity. You're talking about sunspot numbers in the 8 to 10 region, when in a normal solar cycle, your peak would be hundreds. It's named after Maunder and his wife. Of course, being the 1600s, his wife didn't get any credit for it, but they dutifully monitored the solar cycle around this time and found this trough. Now, the reason in popular science and in the media why the Maunder minimum was such a worry for people was that it coincided with what was called in climate circles a little ice age in Europe. Around the same time of the 1650s, the winters were far harsher than had been either previously or since. And many within different communities erroneously thought there was a direct link between the number of sunspots, the solar activity, and this freezing effect really that was happening in Europe. Here is a famous painting I've put in just of the Thames when it froze over. This was a feature of this time. But this link is wrong. It's not correct. The solar output itself doesn't change with activity. You still have fusion whirring away in the center of the sun. And it just happens to be a causal, uncorrelated event. Many climatologists think it's due to volcanic activity that caused this cooling effect, especially given the fact that in the summers, there was no increase in temperature, only a decrease in the winter. So there was a time where the press was getting very worried that we were heading for an ice age because of the sun. but that was never going to happen in the first place. But you know, media sometimes just chases what they think is interesting, not necessarily what's correct. So at the end of the day, we've got no great minimum coming. We've entered into what's called cycle 25. We had our minimum in 2019 where there was next to no solar activity at all, which is frustrating for people like me who book telescope time, go to the telescope, and then there's absolutely nothing of interest to look at. However, NASA and its official committees got together and in September 2020 officially rubber stamped and announced that with an increase in magnetic activity, we're entering into cycle 25. So over the course of the 2020s, we will have sunspots, flares, CMEs that we can point all of our instruments at and get a good look at what's going on in the sun. Here I'm just showing a video that just shows really the difference between the sun at maximum and minimum. And you can see that there is still magnetism in the sun at solar minimum. That doesn't go away, but you have far less of the strong magnetism, these sunspots, which are thousands and thousands of Gauss and really define a lot of the exciting physics. You can see the chaotic magnetic field around it, as opposed to the quite simple bar magnet style in the minimum. So for those that might not know, you say, well, what's the point in looking at the sun in 2021? The fact is that we still, after 80 to 100 years, are searching for that definitive answer to the coronal heating problem. In layman's terms, the coronal heating problem is the fact that as you move further away from the sun's surface and its atmosphere, the atmosphere actually gets hotter. There is more temperature in the high corona in this diagram of 1,000,000 degrees than there is at the photosphere, which is the surface, at 6,000 degrees. So this has been the main problem in solar physics for close to 100 years now, and there still is not that silver bullet, that definitive answer for why we're seeing exaggerated temperatures far from the surface, where all the energy is coming from. This is akin to setting a bonfire, standing 100 meters from it and feeling more heat than you would if you're standing right beside it. The key really, in many people's eyes, is how does the high corona interact with the photosphere, the solar surface, and how does the magnetic field play a role in transferring this energy from below the solar surface right up into those high regions, many thousands of kilometers above the solar surface. The reason really where the focus is driven from is the fact that all of that all of that magnetic field potential drives these explosive coronal events, these CMEs, these flares, that, as I said before, do have a potential threat to our well-being on Earth. They can, in an instant, wipe out our power grids, take down our communications, anything really that runs on an electrical circuit, in theory, if bombarded with enough of these charged particles that come from the sun, can have an effect on our lives. So therefore, the focus is on predicting these events, anticipating them, and in order to do that, you have to really understand the physics underlying them. So with that in mind, the question then becomes, well, how can we observe the sun in a practical and useful way in order to find answers to these questions? So as with all astronomy, now it's the same with every field, there is the debate between, do we put our observatories in space or do we keep them on the ground? You may well be able to infer from the manner in which I speak about the positives of each that I am a ground-based observer and I have my biases in that camp. But as you'll know, in all senses, whether it be Hubble, whether it be Kepler, and in this case, the Solar Dynamics Observatory, there is always a push in astronomy to get our observatories up into space. The reasons, the main reason for anyone who's ever tried to take a picture of the night sky or even the daytime sky is that you can get rid of the atmosphere. You get rid of your clouds, you get rid of your water vapor, you get rid of any dust, any light pollution, and you can get 24 hours observing windows, especially with the sun, by putting your satellite in the right place around the Earth. So rather than traveling all the way out to the Dunn Solar Telescope, as I've done here in New Mexico, and crossing your fingers and praying that the clouds part and give you good seeing, you can guarantee if your satellite is up in space that you will be able to observe the target you're looking for. Another advantage of space-based observing is that you can observe all of the wavelengths that the sun is putting out, from gamma rays all the way to radio waves. You don't have the Earth's magnetic shield blocking anything, so you can look at very high energy effects and low energy effects all at once. When it comes to ground observing, well, the main benefit is that it's cheaper. You don't have to build a rocket, you don't have to send something up into space. You're not concerned about how much anything weighs, how long it will last, how it's going to be powered, because it's right there in front of you. It's an observing bench. That makes it more accessible. If something breaks at the Dunn Solar Telescope, well, the chief technician at the Dunn will fix it. As you remember from the Hubble Space Telescope, if in their case, when their lens didn't work, they spent millions and millions and millions of dollars in order to fix that. Another large advantage of ground-based observing is that there's less risk associated. Now, if you put yourself into the shoes of somebody who's poured 10, 15 years of their professional life into the perfect satellite built to do exactly what they want, then you go to, whether it's Cape Canaveral or French Guiana for the launch of your satellite into space. If you were to be presented with something like, well, this, I think you would be just about ready to retire there and then. So it has happened in the past. There have been rocket sounding missions, solar rocket sounding missions, years worth of work and effort that have blown up on the launch pad. Well, that's not going to happen if you're just transporting something by courier to your telescope. Main advantage of ground-based is that the resolution is better. We can place large mirrors, we can focus a lot of light, we don't have to worry about getting that stuff into space. We can collect as much data as we like because it's all going into hard drives that are sitting right beside us. And something that's not often mentioned is that we can keep technology at ground-based observatories cutting edge. When you put in a funding proposal, whether it be to the American government, to European governments, when that is granted, that is the level of technology that you have to build your instrument. So if you get your funding approved in 2010 and you launch it in 2020, well, your computing is going to be stuck in about 2012 when you bought the computers, when you got the money for it. You're already almost obsolete by the time you get the thing launched into space. Again, not an issue if you're observing from the ground. However, the recent large advantage in going to space is that, well, you can place your satellite just about as close now to the sun as you like. For those of you that will know, this is the Parker Solar Probe. This is NASA's exciting experiment, really, to effectively go, if we were to strap some instruments onto an observing sled, how close can we get it to the sun before things start to melt? Now, they poured $1.5 billion into this project, designed to get 7 million kilometers from the solar surface. So that's into the corona, that's into the solar atmosphere. This is unprecedented distances from the sun. As you may well know, it was launched a few years ago successfully, didn't blow up on the launch pad, thankfully. And in its 7-year mission, it's planned to do 24 orbits of the sun, and in each orbit get gradually closer to the center, using Venus a number of times to speed it up and get it in there. There's a lot of innovative science that went into building the Parker Solar Probe, more than I would have the expertise to talk about. But the simple fact, for instance, that black heat shield that you'll see on the front of it, made of carbon-carbon, is almost identical to the graphite that would be made, they would make golf clubs, tennis rackets out of. It's remarkable innovation to build an instrument that can get that close to the sun without anything melting or falling off, in all honesty. There's 5 instruments on it, and its goals are to get right into the corona, to directly measure the coronal magnetic field, to measure the solar wind, to measure these energetic particles in situ. In general, when we're observing from the ground, we just have photons of light hitting, and we have to infer all the properties of the plasma from that. It's not the case for the Parker Solar Probe. They can literally stick a little bucket out, collect some actual corona plasma, and directly measure these things, which has never been done in a robust way before. For those who are interested, the Parker Solar Probe is named after a very prominent solar physicist, Eugene Parker. It's the first spacecraft NASA have made where they've named it after someone who's still alive. This here is Eugene watching his own satellite be launched a couple of years ago. And it was only, I think, 2 years ago, the woman there who's the mission lead was giving a presentation on initial results. And she was saying that Eugene Parker is constantly badgering her on the phone, looking to get first dibs on the data, because he's very keen to see the theories that he's been working on for all these years finally proven. Even at 94, he still has that keen interest. They sent it with a copy of his seminal 1958 paper, strapped in underneath all of the hard workings. And as many of you may well have known at the time, they canvassed for over 1 million names that were put onto a USB and sent up there to effect for you to visit the sun as well. Its sister instrument that you may also have heard of is its European counterpart, the Solar Orbiter. Again, another $1.5 billion outlay, launched just in 2020, a similar instrument, but with different aims. Now, this instrument is not going as close to the sun. It's going to get closer than Mercury, but what that means is that it can have longer to observe as it passes by. And with the heat not being as intense, as you can see in the schematic at the top, they're able to put cameras into the heat shield. So they're able to directly image the sun at this distance, whereas the Parker Solar Probe's instruments have to hide behind the heat shield or they'll burn off immediately. That means it has a larger instrument suite. It's going to do more science. And they're also, if you can see in this diagram, they're going to take it off the elliptic plane, about 33 degrees off of the plane that the Earth orbits around, to try and get the first direct measurements of the solar poles, which we've never been able to see before. So in terms of initial results, I don't know what time I'm at actually. If somebody can keep me on track with that so I don't get too distracted. One of the initial things they've been able to do is actually get some really high contrast, high interest data on Venus. Now, I'm no Venus expert, but it's really stunning how, as the Parker Solar Probe is transiting around Venus to pick up speed for its next run at the sun, they've just turned on all the cameras, all the instruments, and looked to see what they can pick up. So this is a live image here of Venus as the Parker Solar Probe is screaming around it about as quick as it can. And this is a video I wanted to play for you so that you can hear, hopefully, the Venetian atmosphere as the solar probe passes through it. These are radio waves that they're observing. So what you're actually hearing here are the resonances from the particles in the upper atmosphere of Venus as the Parker Solar Probe passed through it. Now, the solar physicists involved in this mission thought it noise and ignored it, but those planetary scientists got their hands on this and immediately saw it as a very important result in terms of explaining why Venus is different to Earth, despite the relatively similar compositions. So an interesting sort of side result, really, which was of interest. But with Parker Solar Probe having now done about 8 orbits and Solar Orbiter 2 of its orbits, they're producing a lot of data, a lot of unique and interesting data that I won't go into too deep a detail of, but safe to say that they're already transforming our understanding of the solar wind, of what's driving these things. They're being able to directly observe jets and flares at a greater resolution than we've ever seen before. And especially this solar orbiter direct image of the sun. This is the closest any image has ever been taken of the sun. And I hope the resolution of your screen will be able to see what that tiny arrow is pointing to. These are what you may have seen in the press called campfires, which are tiny flares that were detected simply because the instrument was so close to the solar corona. These are potential evidence of the nanoflares that Parker theorized right back in the late 50s. And what is clear just from initial studies is that the sun is so much more dynamic on a small scale than we could have ever anticipated. And the closer we get to it and the better we can see it, well, there's just going to be more to see as we get deeper. But if you really want to go deep, you have to stay on the ground, sadly. because that's where you can get your big focusing mirrors, and that's where you can really start to get your high resolution. Now, for those of you who have been in the IAA for long, I'm sure you've had Mihaly Mathiadakis or someone similar come along and talk to you about DKIST before, because it's a project that Queen's is directly involved in developing the cameras for. But as a quick primer, this is a $340 million solar telescope being built on top of a volcano in Hawaii. Now, for cost equivalences, this is the focus of all ground-based observing. They've poured all the money they have into this, and it's still coming out an order of magnitude less than the Parker Solar Probe, just because you don't have to send anything to space. But the key is that this telescope has a 4-meter diameter mirror. Now, the science behind getting a mirror at scientific quality of that size took a lot of work for these developmental teams, but the current largest solar mirror we have is 1 meter. So this is an exponential increase in the amount of light that we can collect from the sun and focus into our instruments. And what that means, now this is the instrument table at the Dunn Solar Telescope, but it's to give you a sense of when you're on the ground and you're in the thick of it, you get a really powerful beam through your telescope. Now the Dunn Solar Telescope, which is only a 75-centimeter diameter telescope, the beam of light is about 80 to 100 degrees Celsius. You can't get near it as it's focused through. And in fact, you might see there's cans of compressed air on top of the instrument table. That is because in the mountains of New Mexico, there are a lot of moths. And when moths see a focused beam of light from the sun, well, they love nothing more than to fly into it, immediately burn and lie on top of the mirror. So the compressed air is there to blow off any moths that get attracted to it. But the point is that in a ground-based observatory, we're able to split the light into all of its different constituent wavelengths, all of its constituent colors, as you can see in this instance, focus them into a range of different instruments, and then start to look at the solar atmosphere as a whole, from its very base to its top simultaneously. What this DKIST has given us is unprecedented resolution of the solar atmosphere. You may well have seen this when it was released in late 2019. These are the commissioning run images of DKIST. So this is before everything's even working perfectly. And this is unbelievable resolution of the quiet sun. This is the photosphere, the granular, like a boiling pot of water, with these small, tiny, bright features being shown in between them. These are effects we've seen already, but in our current imaging, these bright features are 2 and 3 pixels. They're barely there. But in DKIST, they're extended objects that we can really track and look at. And as somebody myself, I look at magnetic flux tubes like sunspots. This here is a sunspot using DKIST. And if you know anything about sunspots in previous images, the center of them is uniformly dark. The sheer resolution of DKIST is being able to show us that there's actually a whole complex array of brightenings and darkenings going on at once. To be able to resolve on the sun something that's 20 kilometers wide is barely comprehensible. They always say it's the equivalent of being able to resolve a pound coin from Dublin when you're standing in Belfast. That's the best analogy they've come up with. But you can tell from my excitement, as this is my direct field of work, that this is a real breakthrough and of real excitement to us. But observing from the ground, what is the goal of DKIST is really to link the atmosphere together. So the plot I have here on the right, which is from a paper I did as a PhD student, shows what happens when you have these multiple different wavelengths of observing all at once. Is you can take a magnetic feature and you can track it all the way through the atmosphere and start to work out how is this energy getting from the photosphere to the corona? How is it bypassing everything in between? This propagating energy is the key to what they think the coronal heating problem, and it's DKIST alongside the Parker Solar Probe and Solar Orbiter that they hope will really be able to open this stuff up. And I say they, I'm very much part of the group that will be working on this data once it's been released to the public. Just as an example as well, I have here a running simulation of what they think these small-scale granular buffeting motions do in the chromosphere. You have the photosphere in your furthest left panel, your higher chromosphere in the right, and you see that this buffeting becomes a swirling motion, carrying waves, carrying energy up into the chromosphere. And if DKIS can absolve things on this scale, then there will be an exponential growth in our understanding of the sun. I'll skip over that. So I've talked now about really why we're observing the sun, how we do it. But something that commonly comes up, especially in myself, who's a professional astronomer, and I'm sure you've had it over the years from friends or family, is, well, what's the point of this? I've talked about all this outlay in costs, in time, in effort, and people commonly turn around and go, well, what's the point? What's the point in looking at the sun? What's the point in looking at galaxies, doing cosmology, whatever? And these two quotes that I found over the years, to me, are some of the more succinct and best answers to this question. The top quote I'll read for your benefits is from Dr. Robert Wilson when he was at a Senate Appropriations Committee in the US, looking funding for Fermilab. And a rather ambitious politician asked him, well, what's the point in funding this? Why not buy more tanks, more guns, whatever? And his response was, this new knowledge, this Fermilab instrument, has all to do with honouring country, but it has nothing to do directly with defending our country, except to help make it worth defending. So there is always an argument that knowing more, having more knowledge, broadening our horizons is what makes society worthwhile and valid. Below the bottom quote from a Nobel Prize winner in chemistry says that preserving knowledge is easy, transferring knowledge is also easy, but making new knowledge is neither easy nor profitable in the short term. Fundamental research proves profitable in the long run, and as importantly, it is a force that enriches any society with reason and basic truth. So for those with any knowledge of the history of physics, chemistry, biology, you'll know that most of the discoveries that we take for granted today were done with no financial incentive or practical reason in mind. The discoverer of the electron did it purely out of his own interest. J.J. Thomson discovered the electron just to answer the question of what's orbiting an atom. He had no idea that in 100 years' time, the world would be entirely dominated by electronics, all based on his one discovery. So really, as astronomers, we have nothing to, we have no need to justify ourselves, but sometimes it's good to have answers to these things. And many of you will know that over the years, there's been plenty of practical applications to the scientific leaps that have been taken in astronomy, whether it be Wi-Fi, CCD cameras, your GPS systems that are all underpinned by taking distant galaxies for calibration. So the next time you input something into Google Maps, you have a quasar to thank for getting you there relatively accurately. It's not the quasar's fault, though, if it doesn't take you there accurately, I should hazard to say. And then it's easy to see that medical physics has numerous links to astronomy in microwave X-ray and radiation imaging and treatments. What I'm looking to just end this talk on is a little bit about cutting edge research that's being done with astronomy in mind. So as a first example here is techniques they're using to bombard surfaces on your left to release energetic particles that can be used for cancer treatment, to bombard a tumor directly. But they found that you got this scatter from what you were trying to hit, creating this unforeseen effect that you don't want to happen. Well, it bamboozled the medical community for a while until a solar physicist got a look at it and said, well, these look remarkably like solar jets, the observations of which you see here. So once the modelers, the solar modelers got involved, they were able to say, well, I'll just use my models of a solar jet that I already have and solve your problem for you. And that's where modern research is trying to go. Every university is keen on cross-disciplinary research. It's the real buzzword now for anyone who's looking to get a grant. And in the case of QUB, in recent years, we have developed a collaboration with Randox sorry, there's a question, I'll answer it, sorry, at the end. This is my last slide, by the way, so don't worry. This is a collaboration built purely on looking to improve the PCR, cancer, drug, and stroke screening tests that Randox are very well known for. And as I've said, if you didn't know Randox before COVID, I guarantee either in good or bad, you've probably heard their name in the news since. This work started in 2017. The goal of it was simply that for your PCR test that you take from that Randox do, and they also do for a variety of different conditions, it's all based on chemiluminescence. So in effect, the chemists get together, they take your sample, they mix it with a number of chemicals. They taught me how to do it, but I was terrible at it because I've not got that pipette accuracy that you get from a chemistry degree. But when you combine everything together, if there is a sample of what you're looking for, so let's say you're screening for cancer. If there is cancer in that sample will light up. It will emit light, very faint light, not to the human eye, but to a CCD camera, yes. And the amount of light it emits and how long it emits that light for is directly related to your diagnosis. So if somebody's system is full of drugs, it will be bright as it can. If there's a very faint signal, it will only just show up. So the accuracy and sensitivity of these tests is all dependent on the contrast that you can get from these tests. So the exact steps of everything that we've derived are all embargoed and all behind these non-disclosure agreements. But what I can show you here is a simple before and after of what we've been working on for the past few years. The pan on your left is what the Randox imaging camera will take. The image on the right is what myself, Dr. Jess, and a few PhD students have turned that image into using simple astronomical techniques. Because as you know, astronomy is fundamentally just based on getting marginal signals pulled out of your noise. So whether that's a faint star, whether that's an oscillation on the solar surface, in my case, astronomers are the world leaders in extracting signal from noise. So over these past years, we've been able to develop these techniques to improve the accuracy of these tests, the range, the sensitivity, all basically by using techniques that as a solar physicist myself, I would somewhat take for granted. We've been able to get exponential improvements. So there's always applications to astronomy that you can't see coming. This was very much one. I had no plans after my PhD to spend 3 years in a lab at Randox with a lab coat on, but at least it made me look like a proper scientist for 3 years. But these are just a small example of some of the exciting things that can come from the investments that we're putting into our observing suites. So that is me done. As I said, my email address is there. There's a lot of stuff I've skipped over. If there's things you have interest in, I'm happy to fire links or talk about it more. But I tried not to get too lost in the weeds, and I hope I achieved that. And if you have any questions at all, feel free. Otherwise, thank you very much for having me.
Well, thank you, Dr. Grant. That was a fascinating, and if you pardon the pun, illuminating overview of your field, especially there at the end, the biomedical applications. I hadn't realized they were quite so involved. We have one question you may be briefly noted from Paul Evans. Paul, would you like to expand on that?
Yeah, sure. First of all, Samuel, that was absolutely fantastic. Thank you. And the thing that fascinates me about our knowledge of the sun is how much it keeps changing, really, isn't it? You know,
yeah, how little we know sometimes is the worrying thing.
What I learned at school in the 1970s is now completely wrong. And we've got a different understanding. But now, I was wondering, now the great leveler, you talked about ground-based and space-based observation. And in normal nighttime astronomy, you know, a few years back, the great leveler was adaptive optics, and you would shine a laser up into the sky and measure, you know, what was wrong with what came back. and then jiggle the shape of your mirror in real time to try and compensate for it. Does anything like that work with solar observation, or is it problematic?
Yeah, absolutely, it does work. All modern observatories have advanced Shack-Hartman adaptive optics techniques. It's actually easier for us with the sun because we already usually have regions of very high contrast. So in these images here in front of you, for instance, when these observations were taken, you focus your adaptive optics on the high contrast sunspot. So rather than having to shine a laser, you already have a feature in your image that is orders of magnitude different intensity to its surroundings.
Right.
So we're able to use that sunspot itself to configure the light path as it goes in. There is obviously the downside of this is, I think right back at the start, I have an image of the solar limb. Sorry, I'm going the wrong way to get to it, but just to give you an evidence of a more difficult, yes, sorry. So this image, which we took at the Dunn Solar Telescope, there isn't as clear a region of contrast. So therefore, your adaptive optics can at times struggle to have something to lock onto, to focus to. And certainly if your seeing becomes bad, if a cloud comes across, then it can lose that object. But in general, in the field of adaptive optics, solar physics tends to have it a lot easier than nighttime astronomy. We don't have to add any signal in to get it. We're able to just use, the one thing that the sun is not short of is intensity, is light output. So people a lot smarter than myself were able to develop techniques based off the back of that. As you said, as adaptive optics was becoming into vogue, if you will.
Brilliant, thank you. It's good.
Samuel, thank you. That also, I echo what Paul said. Fascinating talking, just what we wanted. Because we, as I said, we have a wide range of levels of background knowledge, and that was just ideal. But just following on from that point, obviously, you don't need larger mirrors for solar observing to collect more light. You want better resolution. So as well as adaptive optics, there's interferometry. So is that being used at all in solar observing?
Yes, we do a lot of spectral, I mean, the vast majority of solar imaging now is spectroscopic imaging, sorry. We're of course able to do it in a different manner to nighttime astronomers because again, we have shed loads of light to deal with. But we are, predominantly what we seek to do is take our light, split it into multi-wavelength scans, full, that's what is able to illuminate the magnetic field and things like that. So almost everything I show you is a image snapshot of multi-wavelength spectroscopic data. Most of the instruments at DKIS, for instance, work by scanning across a spectral line. So they'll pick an element that is very abundant at a certain height in the atmosphere. So calcium, for instance, in the solar chromosphere, image as an absorption line from calcium at many, many different wavelength points across it. And that way you're able to get spatially resolved spectroscopy interferometry, if you will. So imaging itself is only a limited part of what we do. And